And just so you know, Janice said she's going to post things on the website. And I put all the things I'm going to talk about today in this nice handout. It's about 15, 16 pages. And it's going to go through each of the disinfection systems that I'm going to talk about today. So you don't have to write notes and go crazy trying to catch everything, because you're not going to. Because this talk is only 20 minutes.
Excuse me. I didn't catch your name. When
Oh, Don Merhaut. Donald Merhaut. And I'm based out of Riverside.
Oh, okay.
So a specialist out of Riverside. Yeah. So, and my specialty is ornamentals and nursery crops. And my real specialty is plant nutrition. So understanding how fertilizers and plant nutrients get taken up into the plants, how they utilize them in a way to mitigate pollution and runoff of the nitrates. You want to optimize your fertilization. And so when you think about all this stuff, I want to. So I always like to do education and inspiration. So turn a challenge into an opportunity, and that's what we have. Okay, and I always tell people, don't let your attitude towards your handicap be your disability. The guy on the pointer.
It will work on the screen.
Okay, so the guy on the left, his name is Ruben, and the guy on the right, his name is Tony, and he did an Ironman here back last month, and he's his guide. So he swims 2.4 miles, they bike in a tandem bike 112 miles, and run a marathon. So see, anything's possible. So don't let these new regulations scare you. You know, it's an opportunity. Okay, so we're going to go over 4 things today: water storage, debris removal, the clarification, and disinfection. And I'm going to talk mostly about disinfection and stuff. But one thing, when you develop a water recycling system, you have to take into consideration your nursery infrastructure, right? So what do you have? Do you have greenhouses? Do you have beds, parking lots? You know, and what are the requirements? Do you have to capture the first storm event like they did in Ventura, or are there other guidelines and regulations? And they're always changing, right? We know that. It's a little frustrating, but this is something we have to work with. But knowing what you have to capture is going to be important where you put the basins to capture the runoff water. And if your nursery is in a hilly site, which many of you are down here, use gravity to your advantage so that you can have it flow down into the collection basins. There are 2 types of collection basins, really. We're talking retention and detention ponds. Okay, retention ponds are basically lined structures that hold the water, and then you have to pump it back out. Detention basins, on the other hand, are used to collect runoff water, and then it percolates into the groundwater. It's a porous bottom. So that it's kind of like, when I think about detention, think about staying after school and you're in detention for an hour, but eventually you get let go. And so that's what a detention basin is. And in some areas of the state, they want to recharge the groundwater, and that's how they do it. But for our purposes, we're doing retention, and we're collecting the water in a certain area and then reusing it. You need to have multiple collection basins because some of the technologies require that you dredge or clean out the retention basin. And if you do that, you don't want to be down. You want to have another basin there where you can use to irrigate, right? So you want to make sure instead of one large retention basin, you may want to consider 2 smaller ones so that you can dredge one out, clean it, and still have the other one to operate. Okay, keep that in mind. Okay, then debris removal. So when I'm going to talk about the different types of disinfection processes, the cleaner your water is for the disinfection, the less chemicals or energy you're going to need to disinfect. The dirtier the water, the more costly it becomes to disinfect your system. So the next 2 things are going to be about how to get the water a little cleaner before you start doing the treatments for disinfection. And floating debris, most systems aren't going to get rid of that. You have to collect the floating debris or clog filters and pipes, and it'll just increase the cost of your water treatment system. And dirtier water, as I said, requires more chemicals to disinfect properly. So consider baffle systems or filters so that you can collect some of the major debris that comes off. We know that pots blow in the wind and stuff like that, and trash. And you want to get that out of the system before you go to treat it. And then clarification. What's clarification? The problem with clarification, if you're in a soil working in an area where there's a lot of clay, not in the containers, but in the ground, and the water's running freely down through those drainage ditches, what's going to happen is that clay is going to get picked up. And clay stays very suspended. And it takes a while for it to settle out. And if you have a lot of clay in your water, it looks like chocolate milk. It's going to impact some of these disinfection systems more so, some more so than others. But if you chlorinate and stuff, chlorine will bind to the clay particles and become useless. So you want to try to have that clay suspension or any type of suspended material out of that water column before you treat it. And there's different ways of doing that. You can have sedimentation through time by either putting it in canals or sedimentation, your retention ponds, and letting them settle out. It takes a good 24 hours. Or in some nurseries, the bigger nurseries, they use flocculation techniques. They have chemicals which bind the clay and the organic particles and make them heavy, and they sink to the bottom. And so there's one way of doing that. Not too many people do that. But it is something that some of the bigger nurseries have done. The other thing that Dr. Oki is going to talk about is stem filtration processes. And that's another way to get out some of that suspended material. Okay, so now let's talk about pathogen control and how we're going to do this. So you need to learn a little chemistry, but it's real simple. There are many treatment options that are available on the market. Chemically, there's chlorine, copper ionization, UV light, and ozonation. And this is going to kill the pathogens through a chemical process. The other processes we can use are physical, and those are sand filtration, heat, and ultrafiltration. And I'll go through each of those. One thing I always want to point out, regardless of what you use in your system or what you adopt, you may want to develop a small pilot, to make sure that your nursery is going to fit and work with those types of disinfection systems you use. You don't want to spend a lot of money on something that's not going to work, right? So I always recommend doing a pilot system before you spend the big bucks on a larger system for the whole nursery. The other thing is, it's good to test your waters before and after the treatment to make sure you are actually killing all the pathogens, okay? So, oxidizing agents, what does that mean? You know, we talk about antioxidants every day of our lives. We see labels on foods to say, high in antioxidants, eat your blueberries, high in antioxidants. Well, what are we doing? You know, what we're doing, there's different things. Oxidizers kill cells, okay? They break cells apart, they're bad. They're bad for the human body, they're bad for any living organism. In our case, we're trying to kill the pathogens. So we're actually using oxidizers to kill the pathogens in the water. So there's two chemical principles you need to know about to just kind of grasp the way these things work. One is most compounds are stable at an electrical charge of 0. So when a molecule is neutral, it's stable. The other thing is electrons are only stable as pairs. Electrons always travel in pairs. So if there's just one electron, it becomes a problem for that molecule. It's going to try to find another electron. And in this handout, I have a little short story that talks about electrons and free radicals and how that works. So an oxidant is a chemical that takes electrons away from another chemical. And when it does that, it's basically short-circuiting the cell membrane. And so that kills the pathogen. And they originally called it oxidation because originally they thought only oxygen was an oxidant. But they found that other things like chlorine can do the same thing. But they still use that terminology in the literature as an oxidant. Now, the ability of a specific chemical in an environment to cause oxidation is measured as redox potential. And if you go down the road and use ozonation, which we'll talk about, in your treatment system, you will look at your redox and you will measure that value when you're looking at the efficiency and the efficacy of your ozonation system. But only for that type of treatment are we going to talk about redox potentials. It's slow. Okay, free radicals. As I said, all electrons have to travel in pairs, and if they don't, then what you have is a free radical. So it's an electron that's going to try to get another electron. And so free radicals can also, even though it has a molecule may have a charge of 0, if it has an electron that's just 1, then it's going to try to find another negatively charged particle. And it's also going to uncouple electron transport and kill the membrane and kill the cell. So ozone is not a free radical because all the electrons are paired together. But when ozone is broken down, then you get free radicals of oxygen, and that's how its efficacy and that's how it works. Okay, so it's not the ozone itself, but when it breaks down in the water. And we'll talk about that, and again, it's listed in here. Antioxidants are any chemical that protects against oxidation. So we eat a lot of phytochemicals, we eat blueberries, things with pigments usually have antioxidants, and we're trying to protect our own bodies, and that's what that is. So that's where the antioxidant thing comes into this. So in our plant world, we're actually seeking out oxidation processes, not trying to avoid them to kill the pathogens. So let's go through the different ones, and I'll go through the chemical processes first, and then I'll do the mechanical ones. So the first one is chlorination. Chlorination is probably the most common one still for disinfection, and what it does is chlorine in high concentrations will disinfect the water more quickly. Usually you have a residual chlorine that you have to monitor, and as I said before, the initial cleanliness of the water is going to be really important. The dirtier the water, the more chlorine you're going to have to add, so it's more costly. Again, the water pH, it's more stable at a neutral pH with chlorination, and water temperatures. If you have really high temperatures or really low temperatures, it's going to reduce the efficacy of chlorination. And I break these down a lot more in these articles that you're going to be able to go and download on site and print out. And here's chlorination and mode of action. Chlorine plus water, hypochlorous acid plus hydrogen plus hypochlorite. So you got two things going on here. Hypochlorous acid is very strong oxidizer. Even though it's a neutrally charged particle, what happens is all membranes are negatively charged. And hypochlorous acid can get inside the cell. And once it does that, it breaks apart and forms the hypochlorite. So it becomes more deadly. So it's 100 times more potent than hypochlorite in terms of killing the pathogens. The only problem with this is that hypochlorous acid is really the predominant chlorine form at a pH below 6 in the water. And most of us don't have a pH that low. Okay? So most of our action is going to happen from the hypochlorite. And there's 3 different types of chlorine that you can put in your system: sodium hypochlorite, calcium hypochlorite, or chlorine gas. Chlorine gas has regulations associated with it. You might have some issues with that. And then sodium, when you put that into the system, you have sodium in there. In San Diego County, we have issues with high salts already, so adding sodium may not be a wise decision. So the disadvantages is high residual chlorine can injure your plants. So if you put too much in there and you overhead irrigate, for example, you're going to have some injury. Some plants are more susceptible than others. The other thing is herbicides and pesticides are not broken down when you use chlorine. Floating debris removal, of course, the chlorine is not going to affect any of that. That's why you have a baffle system. And then dissolved organic matter is going to bind your chlorine. So if you have a lot of organic matter suspended in your water, you're going to need more chlorine to disinfect it. You need to monitor, and this will go for all the systems, you need to monitor your pathogen populations and make sure you're getting adequate treatment. The advantages are operation costs are low, capital costs are low, exposure time is fast. Some of these systems you're going to see, you're going to need exposure times for like an hour. And when you're dealing with large volumes of water, that may not be a feasible solution for you. And then adaptability. You can use it in small or large production systems. It's very flexible. And there's a lot of knowledge about chlorination. A lot of people use it. The other one that's out there is called copper ionization. And what they do is it's the same thing. It's an oxidizing agent. This time it's copper instead of chlorine. And they insert copper-coated ceramic electrodes into your water somewhere along the way. And then they put an electrical charge through that and releases copper. And so that is how that oxidizes and kills the pathogens. But keep in mind that copper is an essential plant nutrient, right? And so if you get too much copper in your system, you can end up with copper toxicity. And long-term use of copper ionization hasn't been studied that well. And so I'm really not sure of the consequences of that. You may be familiar with copper using it for coolant pads, right? They'll add copper to the coolant pads to keep algae and mildew growing on coolant pads in some of the greenhouses. The advantage is that it's moderate. You need to have an electrode put in or several electrodes depending on how much water you want to treat. But the replacement cost is fairly high for those once they go, and I don't know how long it's going to last. It depends on your water. Installation costs are low because you just have to install these electrodes at some point in your water recycling system. There's no additional chemicals required, but if it doesn't work completely, some people will still use chlorine or some other method to oxidize the water. Few technical components, it's very easy to use. Maintenance, pretty much, it's a low maintenance issue until you have to replace them. And everything is killed with them. And copper ionization will not alter the pH of your water. This can be a problem in some systems. You gotta watch the pH. Space, very small space. It's just gonna put them into pipes wherever the water's passing through, so space limitations. This may be something to consider. And it will kill all the pathogens if done correctly. Okay, disadvantages, some crops are sensitive to copper, so you need to know that and figure out what plants are sensitive to it. Again, it's reduced in dirty water. The more stuff suspended in the water, the more copper ionization you're going to need. It does not remove chemicals, herbicides or pesticides. It does not break down floating debris. Coloration due to dissolved organic matter and such is not going to be removed in your water if you have a problem with that. Clays and other soil particles will not be removed with this. And again, as I mentioned, copper ionization in a closed recirculating system may become a problem if it gets to high levels of concentration. The next one I'm going to talk about is a chemical process as well, but it's a physical component. It's ultraviolet light. So we worry about UV light, right, getting sunscreen and protecting ourselves from skin cancer. But ultraviolet light can also be used if you have really clean water systems. So if you're doing hydroponics where you don't have soil and your water is not running off into the actual vegetation, then your water is going to be clear. And this is where UV light can work. So the duration time is 1 minute to 24 hours, depending on how clean your water is. Hydroponic systems, I've seen it function and it works. You can use 3 different types of UV sources: low pressure mercury vapor lamps, xenon flash lamps, or Excimer lasers. So you can use these. Sometimes, again, people come through and will do this in addition to another type of oxidation process. The advantages of the operation costs are low if the water is already clear. Installation costs are relatively low, like the copper electrodes, because you're just putting them in one point in your treatment system, so you're just inserting these electrodes and the water passes through. There are no chemicals in this, so that's a plus. Maintenance is low, pathogens will be killed. There's no effect of ozonation on your water pH, so if you have issues with your water pH, it's not going to change anything. Space, very small space for this, and it will kill everything in it, and it's non-toxic to the plants. The disadvantages are your exposure, well, it's up the top. Chemically, you can denature chelates. Chelates, if you use chelates in your micronutrient blends, chelates are sensitive to light. So this is going to denature your chelates, and your nutrients are going to precipitate out. So you might see like an orange residue at the bottom of a tank, and that's your chelates precipitating out, and you're no longer functional. So you have chelates in your system, this may not be a thing for you. Again, effectiveness is reduced by dirty water because the UV light has to shine through the water column. Herbicides and pesticides do not get removed, but they may break down, and you'll have to check with the manufacturer to see what the consequences are and if they are sensitive to UV light. Dissolved organic matter is not going to change. If you have tannins and stuff in your water, this isn't going to eliminate that. In fact, it's going to make ozonation more difficult because the water is not clear. And then exposure time will vary by 30 seconds or longer depending on the clarity of the water. Okay, next one. Ozonation. Let me see here. Yeah. So ozonation is the next one, still an oxidizing agent. And again, ozone, that's incorrect, that shouldn't be, we're talking about ultraviolet light. But ozone, you're still going to you're going to treat the water with ozone, and you can do, I got this wrong. Where's my other other slide. So ozone, what ozone is, that was the UV light one. What ozone does is ozone is injected into the gas, injected into the water, and the ozone breaks down, and you get the oxidation on the pathogens just like you would with chlorination. And so ozone is nice because it breaks down to oxygen, so there's no residues. There's no additional chemicals needed for ozonation. It's easy to monitor because you're measuring the redox potential. So there's a meter that you can measure the efficacy and the intensity of ozonation. The maintenance is low unless the oxygen source is not clean, then the electrodes must be cleaned. So we run into problems with ozonation and some of these other ones with electrodes if we have a lot of calcium and stuff in the system because it can get on the electrodes. And then it does break down pesticides. So you have to check with your manufacturers to see what pesticides and herbicides are in your system. Or you may want those broken down anyway. So but you'll have to check on that. The disadvantages of ozonation is you may have to have your water exposed 20 minutes to an hour to achieve 100% mortality of the pathogens, which means you're going to have to treat the water and hold it. Space allocation, you're going to need collection tanks for this. Okay, unlike UV where you're passing a light through and the water's moving, with ozonation you have to have the water in there and ozonated and wait until it's completely kills the pathogens. You have to think about the electrical cost for this system. Ozonation will also increase the pH, so you have to worry about that. Water acidification may be necessary after you go through ozonation. So you have to check the pH of your system as well, of your water. Some pathogens may be more difficult to kill with ozonation because they insist, and it's like a protective barrier, and it may be harder to kill some certain pathogens. Again, with ozonation, it may react with some of your micronutrient chelates. So it may, once it changes the chelate structure, then the chelate's no longer functional. And again, if you ever question whether your chelates are being impacted in some of these systems, you usually will see a residue in the bottom of the holding tanks. It'll accumulate, and that's your chelates breaking down and precipitating out. It also may precipitate some of these other nutrients as well. And plant toxicity. So ozone levels should be below toxicity levels before applying to the water. So you have to put it in the holding tanks, and it has to dissipate, or you may get ozone damage to some of your more sensitive plants. Okay, let's see here. So heat treatment. Now heat treatment is a physical thing. Okay, it's not a chemical, it's not oxidation. And heat treatment is just basically heating the water. And the hotter it is, the faster you can kill the pathogens, of course. There's nothing scientific here. You put in metal heat exchangers along the water treatment system. And the water pH may be acidified somewhat to prevent calcium accumulation on the exchangers. So when you put these heaters in there, you get some calcium buildup. So if you have a lot of calcium in the water, that may be a problem. Acidification before treatment may be essential. The other problem with heat is it takes energy, and the water has to be cooled before you apply it to the plants. But no chemicals, no additional chemicals. If you do heating correctly, it'll kill everything. It's safe for plants once the water is cooled sufficiently. In some parts of the country, they actually use the hot water to heat the greenhouses. I'm almost done. Yeah. And then heat treatment, the disadvantage is you have to cool the water. The treatment period can be longer if you have your temperature isn't too high. You need to have space allocation for the water to cool, just like you had with ozonation. So if you have space limitations, this is a problem. You need to heat the water somehow. That's going to cost money. You need to really acidify before you heat it because of the calcium buildup. And it doesn't remove clay and silt, and your chelates, again, in this process, will be physically distorted, basically, and they will become precipitated out, and they won't work. Pesticide breakdown depends on the pesticides and herbicides you're using, whether they'll be inactivated or not. Okay, and then the last one, I saved the best for last, I think. So there's reverse osmosis, nanofiltration, ultrafiltration, and microfiltration processes. We're all familiar with RO, right? RO water is you're passing everything through a membrane, and there's tiny holes in that membrane. And so what you're doing is you're pushing the water through a membrane. And what those different types are just basically defining the pore size for those membranes. So this is in the handouts, but the larger the pore, the more stuff can pass through, right? The smaller the pore, the fewer things can pass through. But you also need more energy to push the water through, so it's going to cost you more money. So RO is very expensive because you have very small membranes. And so what I did, to make it easy for everybody, because when I looked at these membrane sizes, nanometers and stuff, I'm like, what does that mean? So I kind of got things broken up for you. And so these are the different types of membranes: reverse osmosis, nanofiltration, ultrafiltration, and microfiltration. This is the pore size. Reverse osmosis is 0.1 nanometers, all the way up to 100 to 10,000 nanometers, right? So this describes the pore sizes for these. The cost is high because you've got such tiny pores. As I say, it takes more energy to push the water through a smaller membrane. The advantages and disadvantages. So when you do reverse osmosis and you have fertilizer in your water, you're taking all your fertilizer out of your water. So that may not be the option for you, but it does get all the pathogens. Nanofiltration will remove some charged ions, but it also may remove some chelates. So if you're using micronutrient chelates, they're pretty big molecules, so even nanofiltration is going to take those out. Ultrafiltration, a little different. It will remove bacteria, fungal spores, and some nematodes, because viruses may not be removed because they're kind of small. And so this system may not work as well for viruses. Microfiltration requires the least amount of energy, but many pathogens will not be removed. So if you want to know what sizes these organisms are, this is a chart that just shows you the different types of molecules and pores and pathogens, and what their weight is and what their size is. So if you look at these two charts, you'll be able to see what can be removed and what can't. One thing to know is there's no correlation between weight and size of a molecule. Some molecules are really dense, and so they weigh more. So there's not always a direct correlation. So that kind of helps you get your brain wired around these ultrafiltration and nanofiltration processes by knowing what size these things are. One thing with membranes is you're going to have to flush them. You're going to have to clean them. Once they get really dirty, you're going to have to back flush them. So there's that problem associated with them, and depending on how dirty your water is will dictate how often you have to back wash these things. And then you're going to have to dispose of the residues that are in there. There will be need to replace, but again, it's going to depend on how dirty your water is that you're treating. So a lot of these systems will work really well for hydroponic systems where the water's a little cleaner. So with that, I'm done. But everything is in here, so you don't have to memorize stuff. I can't memorize things. I don't know about you all, but I can't. So I don't want you to either.
Can you send that like